So lastly, we have some properties of binomial distributions and examples. So if we want to graph binomial distributions, we may do that easily with Excel. So for example, what we may do is that when we have a n that is fixed, we may want to test what's going to happen if their p's are different. So here we are trying to reveal the probability functions for different binomial distributions. Their n are all fixed to 20, but their p are 0.3, 0.5, and 0.8. So let's look at the first one. Here we have a blue curve. So what is that? The blue curve is asking us about what is the probability function for a binomial distribution where n is 20. I have 20 trials, and for each trial, the probability of getting a success is 30%. Okay? Then the height here is just the probability that we are talking about. So for example, if I want to see what's the probability for me to get 4 success, okay? I do 20 trials, and if for each one I have 30% of probability to win. What's the probability that I win 4 times out of 20 times? Then I point to 4 here. Okay, I can see the probability is roughly 13%. What's the probability for that to happen when my x is 5? Then I do it again. Well, the probability gets higher. It's about 17%. So these are the meanings of the curves. For the curve, it is highlighting the probability for each possible values in the binomial distribution. So here we may compare the 3 curves to understand some different things. For example, we have 2 independent sequences. The first one is each time we win with probability 30%. The second one is that each time we win with probability 50%. Let's compare their probability of winning 5 times. Okay? So if we are talking about 5 is here. And we can see that in the second distribution, the probability is just about 2%. And in the first distribution, the probability is about 18%. So that's a huge difference. And why is that? Well, if you think about the physical meanings of binomial distributions, then you understand why. In the first case is that we try 20 times. Each time we have 30% of probability to win. Okay? Then if we want to win exactly 5 times, well, quite somewhat possible, right? Because each time we have 30% of winning probability. So it's not very high. So roughly speaking, if we want to guess whether we're going to get 10 success, 15 success, or 5 success, I think the 5 is the most likely outcome among the 3. But if you have 1/2 chance of getting a win, each time you have 1/2, each time you have 1/2, then when you try 20 times, most likely you will get 10 or 11 or 9 success, right? It's not very easy for you to get just 5 success. Each time you have 1/2, then you try 20 times, and then you just get 5 success. The probability is rare. So on the other hand, if we are asking about the probability of winning 9 times, then we can see the second probability, the second distribution gets a higher probability. Okay? So all those things make sense. And actually, if our P goes up, then the curve would shift to the right. And as you understand that this curve somehow means distribution, so that means for the curves at the right, that distribution has higher probability to get high values. And that makes sense, right? When you try 20 times and each time you have a very high winning probability, 80%, then it's more likely for you to see 16, 17, 18 compared to other distributions. Okay, so here we have an additional question asking you about what's the skewness when P is 1/2. Well, when P is 1/2, your distribution is of course symmetric, because everything is 1/2, 1/2. You have some probability to lose, some probability to win, 1/2, 1/2. So it's more likely that you will see exactly, for example here, 10 successful outcomes. Maybe you have some cases that you will win just a little time. Sometimes you win a lot of times, but the probability is roughly the same. Okay, so let's see some example. Suppose we have a machine. It produces chips with 6% defective rate. So roughly speaking, if you produce 100 chips, 6 out of them are not good. Okay, so now a company purchase 20 of the chips. Now let's try to ask how many defectives we may see. So it's possible for us to see no broken chips, 1 broken chips, 2 broken chips, up to 20 broken chips. All are possible. Even if the probability is just 6%, it's still possible for you to see 18 defectives, 19 defectives. Well, that's possible. But anyway, we may count the probabilities. So we have X. We say it's a binomial distribution with 20 trials, and for each trial, the success probability is 6%. So here we define defective as success because that's the target that we are looking at. So now we may calculate the probability that none is defective is this one. Okay? We have 20 trials. In 20 trials, none of them should be a success because we want all of them to be good products. So we have 20, choose 0. And then 0.06 should occur no times, and the 94% should occur 20 times. That's around 29%. If we are asking about what's the probability for no more than 2 outcomes are defective, then we count the probability for no defective, the probability for 1 defective, and the probability for 2 defectives. Okay, then that's 88%. So what does that mean? That means in this particular production process, if we produce 20 chips, it's very unlikely for us to see 3 or 4 or 5 errors. It's more likely for us to see 0, 1, or 2 errors in this particular example. Okay, finally, let's reveal to you about the expectation and the variance of a binomial random variable. So if your X is a binomial random variable with n trials, and each trial you have a probability P to win, what's the expected number of wins you will have? Well, just n times P. So that's not very weird, right? You toss a coin 20 times. Each time you have a chance of 1/2 to see a tail. Then what's the probability? What's the expected value? What's the expected number of tails you may see? 10. Because you have 20 trials. And in expectation, every 2 trials you see a head in expectation. So in 20 trials, you expect to see 10 heads. That makes sense. Or also, here, you have variance. Variance is n times P times 1 minus P. So we probably don't have a very intuitive way to explain this. But if you think about P times 1 minus P, you realize that this has something to do with Bernoulli sequence, right? For a Bernoulli trial, our variance is P times 1 minus P. Now we have n independent Bernoulli trials. So for each trial, when we do one more trial, because it's independent, so we independently add some more variability into our process. When you just do two trials, it's easy to predict the outcome. When you do n trials, when you do 10 trials, 20 trials, 100 trials, it's harder to predict the outcome because there are more possibilities. So that's why when you have more trials, you have a higher variability. And also, P times 1 minus P is still here. If you do a lot of trials, but your P is very high, still it's easy to predict how many success you will see. It will be high. If you have P that is very low, then still it's easy to predict. it will be the hardest to predict the number of trials you may get if your p is exactly 1/2. And the intuition is just that with the Bernoulli sequence. Okay, so that's our introduction to binomial distributions.